Hello, Year 12s. This is part 2 of Learning Intention 33, which is automatically write basic integrals. In the last video, I added exercise 9a, questions 5, 7, 10, and 11. I insist that you have a go at least 4 or 5 from each question, at least. And if you need to practice more to get it, practice more. So that's exercise 9a. So we're going to look at a few examples, and I'd say they're fairly tricky, of applying our integration formulas. So in the previous video, I gave you a bunch of formulas to learn, and here we're going to look at how we actually use them. And I'm going to get trusty Kaz calculator to check our answers. I'm going to show you how to integrate there as well. So the first one is going to use knowledge from Year 11 methods. So this is a Year 11 standard integration problem, but it's tricky. So we've got 3x squared plus 2x minus 1 on x squared. A very common thing I saw in previous exams was people treated each term here and integrated each one. So they integrated that, and that. Not quite. You can't quite do that. You have to have each term split up. So this divided by screws you up here. You can't just integrate each bit. You have to split it up. I'll show you what I mean. You can divide each one by x squared. So using a bit of algebra, you can split up the denominator. So it becomes 3x squared on x squared plus 2x on x squared minus 1 on x squared dx. Okay, why can you do that? I'm going to show you quickly why you can. Because it's such an important skill. Let's say I have 6 divided by 2. We know that's 3. Great, who cares? It's 3. Well, I'm going to prove to you that you can actually do this, because 6 divided by 2 equals 2 plus 2 plus 2 all over 2. Well, division is distributive. You can divide each individual bit. So you can go 2 divided by 2 plus 2 divided by 2 plus 2 divided by 2, which equals 1 plus 1 plus 1, which equals 3. So you're allowed to do this. And I've just shown you an example of why. Hopefully that will help you remember that you can split up the denominator for each term. Then we can use our index laws. So, well, x squared divided by x squared, they cancel. So we get the integral of 3. X divided by x squared is 2x to the negative 1. And we're left with x to the negative 2 dx. Alright, now we need to add 1 to each power and divide by the new power. So we get 3x. Ooh, this is interesting. We've got this negative 1 business here. We've got to be careful. We've got to remember our natural log integration. So I lied. This is not a Year 11 standard question. This is a Year 12. This is actually quite tricky. We've got to remember our natural log. So the formula you had before, when it goes to negative 1, you have to do the natural log. So it becomes plus 2 natural log of x. And we can do our absolute value bars if you like. If you're worried about remembering that, if you're thinking, how am I going to remember that I don't add 1 to the power and divide by the new power here? Like, how do I remember that? Just think about it like this. If you add 1 to the power, that becomes 0. And if you divide by 0, alarm bells should be ringing. You can't divide by 0. So if you ever catch yourself integrating and then dividing by 0, think, oh, maybe I needed to use the natural log function. And then over here, we add 1 to the power and divide by the new power. So it's minus. So we've got to add 1 to the power. So it becomes x to the power of -1 and divide by -1 plus c. Let's tidy this up. We get 3x plus 2 natural log of x plus 1 on x plus c. Alright, how do we know that's correct? Kaz can tell us. We'll see how we went. There's a shortcut which can help you get the integration going. So you can go to calculator and you can go shift plus for integration. And he gets this thing up here. Shift plus does that. We don't have terminals, so we can leave the terminals. But we do have 3 times x squared plus 2 times x minus 1 divided by x, divided by x squared. We do have to put our variable in x. Let's see how we did. 2 natural log of x plus 3x plus 1 on x. And it leaves out the plus c because the calculator gives you an antiderivative, like an, like it's an antiderivative. This is the antiderivative plus a constant. So I've gone through that before. Beautiful, that's correct. That's one example down. Let's have a look at another one. Alright, I didn't mean to choose such a tricky one to start off with. Let's look at something like the integral of 3 cos pi x on 2 dx. Now, I don't really remember formulas for these, so I'm going to take you through my thought process of how I actually do this. And if it doesn't help you at all, please memorize the formula. If it does help you, maybe the thought process will help. So how do you do this? This is what I think to myself. I think, well, I know that sine diffs to cos. So taking the derivative of sine, you get to cos. So cos must integrate to sine. So sine diffs to cos. So cos must integrate to sine. So I know that the answer is going to be sine something or other. And I know I have a constant here. So constants, they sit out the front. Alright. What else do I know? Well, I know what's in the brackets stays the same. And I know that I take, I divide by the coefficient of x. That's what I know as well. I divide by the coefficient of x. So I have to divide by pi on 2. So I can do that like this. So I have to divide by pi on 2 plus c. And then the 2 jumps up there, so it becomes 6 on pi sine pi x on 2 plus c. And you're probably thinking, well, okay, great, but how do I know that's the answer? Go backwards. Take the derivative of this. Let's check it. Let's take the derivative of 6 on pi sine pi x on 2 plus c. Let's take the derivative of this. Well, sine diffs to cos, and the coefficient gets multiplied by what's out the front. Those cancel. 6 divided by 2 is 3. there you are. That's one. Whoops. That's one way to check it. That's the same thing. Another way is your CAS. So have lots of ways to check your answer. You might look at it and go, is this right? I don't know. You can take the derivative to go backwards, use your CAS, check that you've got the right answer. And we can remember our shortcut, which is Shift plus. And we're doing 3 times cosine. So trig cos pi times x on 2, wrong one, escape, pi times x on 2 x gives you, yeah, there we are, 6 on pi sine pi x on 2. Beautiful. Got the correct answer there. So a number of ways to check your answer. Let's have a look at another example. And the heading and the learning intention is slowly disappearing every time I clear the screen. Let's have a look at something like the integral of -10 7 minus 5x to the power of 4 dx. Now I gave you a formula for this, so if you need to use the formula, please do, but I'm going to show you my thinking of how I handle it. First thing I do is I rewrite it so I don't make any silly mistakes in the same line. Now if you remember, this is one of those ones where there's a coefficient of x inside the brackets. So you do what you usually do, you add 1 to the power and divide by the new power. Let's add 1 to the power and divide by the new power, but you also divide by the coefficient of x. That's the extra little bit. That's the extra little bit. You've got to add 1 to the power, divide by the new power, but you've got to divide by the coefficient of x as well. So that becomes, if we tidy this up, it's -10 on 15, 7 minus 5x to the power of -3, which equals -2 on 3, 7 minus 5x cubed. What am I doing? I'm getting out my CAS. I want to check my answer. That's a cubed, by the way. Looks kind of funny. Plus C, I probably need a plus C there. Let's use the CAS. You should be able to tell me the shortcut now. Shortcut is Shift plus. Let's do this. -10 divided by 7 minus 5 times x, 7 minus 5 times x, and that's all cubed dx. Let's see. Oh, whoops, it's to the power of 4. Let's fix that. Back to the power of 4. Okay, we're struggling here. To the power of 4. There we are, we've got the right answer there. -2 over 3. Oh, what have we done there? Oh, okay, they've done, oh, look, they're the same answer. They've been really clever. They've been very clever. See how there's that, we've got to get rid of that negative sign here. Well, what they've done is they've taken out the negative from down the bottom, and the reason you're allowed to do that is because it's cubed because negative 1 all cubed is negative 1. So you can take out the negative and then you can cancel that. I don't think there's much different. I don't see the difference. Like, they're both fine. They're both correct. But you can take out the negative sign there. Very sneaky. Very tricky. Alright. Another example. Integration. Lots of integration. Let's look at something with a natural log. I don't even know where are we up to example 4? I don't even know. So much integration happening here. Let's look at a natural log. So, well, not a natural log, but the answer is going to be a natural log. So how are you meant to integrate that? Well, you should notice if the x is in the denominator and it's a linear term, so it's just x sitting by itself, it's not x squared or x cubed, it's going to be a natural log thing. The way I think about these is just take the natural log. Just take it. Don't think about it. Just take the natural log of whatever's down the bottom. Constants kind of sit out the front. They tend to. And then you divide by the coefficient of x. That's generally what you do. Take the natural log and you chuck that in there. That's a coefficient really, it sits out the front, and then you divide by the coefficient of x. It's very similar to the previous one in a way. And then it's negative 3 on 11 natural log of the absolute value of that plus c. How do I check if it's right? Let's go the other way. d dx. And I'm going to be very imprecise and just assume that I can drop the absolute value bars just to do check my answer. So diff over the original, yeah? Diff over the original. Negative 11 on 6 minus 11x times negative 3 on 11. Well, you can see what happens there. The negatives cancel and the 11s cancel. The negatives cancel and you get 3 on 6 minus 11x. There we are. I've checked my answer. And I have one more example for you. One more. And this is how to integrate the exponential function. So let's say the integral of 3e to the x on 2 dx. So with differentiating, you times by the coefficient of x. So if I had like d dx of 3e x on 2, you'd be laughing because you're just like, oh, it's half times that. So you took the coefficient of x and you times it by that. Here you take the coefficient of x, which is a half, and you divide by it. Plus c, and that becomes 6e to the power of x on 2 plus c. How can I check my answer? I can take the derivative of this. Let's check. Let's check the answer. Bring the bring the coefficient down. So that's 6 on 2e x on 2, which is 3e to the power of x on 2. Constant goes away. It's a bunch of formulas. It's not too bad. It's just a bunch of formulas. And there are some patterns in the formulas that can kind of help you memorize them. If the tricks don't help you, memorize the formulas. If they do, try to see the patterns as well, because there are a lot of recurring themes or recurring ideas with integration. Like with derivatives, if you like, you can think of derivatives are kind of like minus and division, and integration is kind of like addition and multiplication, and they're all kind of opposite. Like if you're taking the derivative and you're timesing by something, when you take the integral, you tend to divide by something. Coefficients tend to sit out the front. And yeah, there's just some recurring patterns. So with a bit of practice, you should be able to see the patterns. But to start off with, it'll require a lot of practice. So make sure you do a lot of questions. And if you have been, Thanks for watching.